Hi, Viper Chemistry students. Let's take a look at the periodic table and some of these ideas. Now, there were some historical figures that played a role in what has now become the periodic table, the modern day periodic table. So, this goes back really to the early 1800s. Oberreiner and some of these investigators would take a look at the elements that they were, that had been discovered and what they knew about those elements and their properties, and then began to group them into similar properties according to elements that had similar properties. So, really, though, Mendeleev was the giant here. His big thing was he was actually able to make predictions about elements that had not been discovered yet. So that's huge. Um, so as time progressed, really the biggest contributions came more or less in the middle 1900s. So, and then that leads us to today and what we know about the periodic table, and it continues to be refined and in terms of like just the properties of elements and how in each group, the way the periodic table is arranged by groups, which really what we're talking about here is the columns that you see. Uh, so when we look at, for example, the first column, which has hydrogen, lithium, sodium, potassium, the column on the left, we could compare that to, let's say, the column on the far right, which has helium, neon, argon, krypton. Now, the point is that these columns tend to have elements that have similar properties. Now, what have we discovered about that, and why is that so? So what it turns out is that the good old electron configurations that we've been working on, so at this point, everybody should know how to do electron configurations. It's just the way the electrons are arranged in orbitals and so on. But the point is that it's really the electrons that determine the properties. So from this point forward, this is where we go. And a term that you will hear repeatedly are what is called the valence electrons. And so these are the electrons that make up the outer energy levels, which really that equates to the s and p orbitals. Okay, so you are going to see, how this s and p orbital configuration of electrons plays a role in not only just the element properties, but also what elements combine with each other. That's the important part. Elements that form compounds, elements that form molecules, are going to do so based on their valence electrons, which again are the outer energy electrons. So here you see this broke down into numbers. So you can see on the far left, those would be ones. Really what that one means is that's one electron available in the outer energy level of the s orbital. And you could, like if we moved over to the p block and we looked at the row 7a, that means that there would be 7 electrons in the outer energy level, which really they need one more to make 8. So here's a good thing to learn about chemistry. It's very, very important that a lot of nature depends on filling up the p orbitals. So like, for example, if you have your 2s orbitals filled, and then you have all of the 6p orbitals filled to complete a total of 8, that means that in nature we see then a stability. So let's look here. So that's called the octet rule. Octet meaning 8. And if there are electrons that fill up the s and the p and have reached 8 electrons, then they become very stable. Otherwise, if they're not there yet, then they're unstable, or they'll want to react with other elements. Okay. All right. So we'll kind of end there, but again, the idea is that the octet rule is that when all electrons have met the full 8, they have reached a stability. And if they haven't, then they tend to be reactive. All right. Thank you for watching, and we'll talk to you later.